So Wittig reagents, which were named after the German chemist George Wittig, who lived from 1897 to 1987, are an important class of compounds because they are used to synthesize alkenes. A Wittig reagent is shown here. And so if we look here, this is a Wittig reagent. And it's characterized by the carbon-phosphorus bond. Now, this is the first time we've really done anything with phosphorus. Phosphorus is a really useful compound, particularly in biochemistry, and you'll do a lot with phosphorus there. But this is the first time we've seen phosphorus. And when we look at a Wittig reagent right here, that's what I wanted. When we look at a Wittig reagent right here, it's important to see that the carbon bears a -1 formal charge, and the phosphorus atom here bears a +1 formal charge. Now, also notice that a Wittig reagent is an iliide. Now, when we talk about what an iliide is, right, it's characterized by adjacent charged atoms. Okay, and so because we have that +1 charge on phosphorus and then the negative charge on the carbon, it's a iliide, but because we have a +1 charge on the phosphorus there, this is specifically, if we want to get really specific, a phosphonium iliide, or ylide. So how does this affect our chemistry? Well, that -1 charge on the carbon makes the Wittig reagent a strong nucleophile at the carbon atom, which you can see there. Remember, we have strong nucleophiles with these red highlights, okay? And it's written there for you, strong nucleophilic carbon. So normally a structure with adjacent positive and negative charges is a weak contributor of two resonance structures, and the stronger contributor is usually the one where the atoms are connected by a double bond and each atom has a 0 formal charge. But in this case, the carbon-phosphorus resonance structure is the weaker contributor, right? So we're looking at the resonance structures here, and everything we've learned about resonance structures so far is to say, hey, look, this would be the stronger one if it was like a carbon-carbon bond. But when we have phosphorus here, all of a sudden, this is not the bigger contributor of the resonance structures. And the reason that is because the pi bond that makes up this carbon-phosphorus double bond would require the interaction of orbitals from different valence shells, okay? The second shell of carbon, so it would require the overlap from the second shell of carbon, and then for the phosphorus, it would require an overlap of the third shell of the phosphorus. And so that's just very, very difficult, okay? And because we have these, because it would require overlaps from these different orbitals, the result is a really weak interaction, and there's very little stabilization relative to the atomic orbital energies. And so what that means for us then is this then is the major contributor. And that's really what we're going to focus on. So this is a Wittig reagent. Now, I want you to notice also the phenyl groups here of the Wittig reagent are often abbreviated as C6H5 or just pH. You can abbreviate those as you want, right? And you can see there are 3 here. I tend to abbreviate these because, honestly, drawing those out is pain. Now, I want you to notice here that you can also have an R group or a hydrogen, or a R group or a hydrogen. I want you to notice the R prime, which means these R groups can be the same, but they can also be different. And that's what they're indicating there. So I know there's a lot going on with this. I want to show you some examples. This is an example of how we would draw a Wittig reagent. Again, this is an example where we've got 2 R groups here instead of hydrogens. These R groups happen to be the same instead of different. I want you to notice how those aromatic rings have been abbreviated as well. So that's our Wittig reagent, and this is a Wittig reaction. Now, the primary importance of Wittig reagents is in their reaction with ketones and aldehydes, which, since this chapter is focusing on ketones and aldehydes, it makes sense that it's here. So what we have here is if you use a Wittig reagent with a ketone or an aldehyde, that's a Wittig reaction, okay? And so what we see here is a joining of two carbon containing groups by a carbon-carbon bond, okay? And so what we have here is we have this carbon here, and it's got a double bond to the oxygen. And as we go through this reaction, what you need to notice is now we still have that same carbon group. We have a double bond, but now we're double bonded to the carbon that came from this Wittig reagent here. So when we look at this group here is now attached here. And I know they show you in red, but there's a lot going on in red, so I wanted to block that out for you. So one group comes from the Wittig reagent, and the second group comes from the ketone or the aldehyde. Notice, right, that newly formed carbon-carbon bond is between the original carbonyl carbon, like I pointed out, and the original phosphorus carbon. So in another way to say this, the carbon double bond oxygen of a ketone or an aldehyde is converted into a carbon-carbon double bond, okay? And so now I want you to just think for a second about what this does for us. We just did electrophilic addition reactions in the previous chapter. So if you walk into the lab and all you have is an aldehyde or a ketone and you really need a double bond to do an electrophilic addition reaction, we have the opportunity now to take an aldehyde or a ketone into a double bond and do an electrophilic addition reaction. Let's look at this mechanism. Okay, so we're going to do the mechanism for the previous slide. So I need to redraw my reagents. So predict the product basically on the previous slide. And it's an aldehyde, so there's my double bond O. Now, I want you to notice when I draw in these reagents, and I'm going to draw phenyl groups here because you can use phenyl or you can use C6H5. Either is fine. And we draw to the carbon. You need to make sure that you draw out these R groups that are here, right, on this carbon, because that's going to help you predict the final structure. I don't want any final structures with R groups, and so that means I don't really want R groups here in the mechanism. So while you can abbreviate these with anything you want, you need to not abbreviate these with R groups, okay? So here's what we're going to do. The first thing we need to do is we need to identify things that are nucleophilic or electron rich, and then the electron port areas they would attack. When we look at this, we have a negative charge on that carbon. That's a nucleophile. And we remember over here that this oxygen is really electronegative, so it's going to withdraw electron density, and it makes this carbon partially positive. So negatives and positives are attracted to each other. They like each other, so these electrons are going to come out, and they are going to attack that carbonyl carbon. And then those electrons are going to be bumped up there to the oxygen. Now, we are going to follow our arrows and see what new bonds we make. Now, that's a nucleophilic addition step. But what we're going to see here is a single bond because those oxygens have jumped up. That means that's going to be a negative take that, move that over just a little bit. Now we have a new bond between the carbonyl carbon and the carbon of the Wittig reagent. We are going to keep our CH3 groups here. And there we are. Okay. Now, at this stage, right, this phosphorus still has a positive charge. I left out my positive charge. Go back and fix that. Don't be me. Right? So, because that positive charge helps us with the next step. And so what we see here are these electrons on the oxygen, right, are attracted to that positive charge and they form a bond. And so this is a coordination reaction. And now what we have is a ring. So we have a ring with the oxygen. Comes over here to the phosphorus. Come down here. And then we have our 3 phenyl groups. Okay, so that's what we have as far as our ring. Now, that's a 4-membered ring. It is super, super strained. Also, I meant to give you a definition. So this is called an oxaphospentane, right, with the ring, okay? And then over here, this is called a betaine. Okay, so we've got a lot of strain, which means it's very reactive. It's going to go through an elimination reaction. And in this elimination reaction, what happens are that these electrons, and it's concerted, these electrons go there to form the double bond, and these electrons go up there, okay? And so that's an elimination reaction. Now we have our double bond there. Now, we're also left with the phenyl, and I'm going to shorten this just to say phenyl 3, phosphorus. I got a little wild with my electrons there, but you get the idea, and oxygen. So one of the things that's interesting here is that's a pretty strong phosphorus oxide bond. It's like 537 kilojoules per mole. So it's particularly stable. Now, I want you to notice that we are forming a new carbon-carbon double bond. And I'm sure the burning question in your heart is, hey, Dr. Pierce, we formed a new carbon-carbon double bond. I bet that means we can have E and Z stereochemistry. And you would be correct. So, if the E and Z isomerization exists about the carbon-carbon double bond, because you know it doesn't always exist, but if it does exist, then you do end up with a mixture of 2 diastereomers. That stereochemistry really can be explained by the first step of the mechanism, which I can't go back because if I go back it'll skip. But if you look back at the previous slide, what you can see is that when we look at that carbonyl containing compound, it can either be attacked from either face, so either side, right? Often what does happen when we look at this in literature is that one diastereomer is heavily favored over the other, but predicting which one is difficult. It's not necessarily intrinsic, and so it's really outside the scope of this course. But if that's something that you are interested in, particularly, we can have further discussions in my office and we can look at the literature. But right now, all I want you to know is that it has a mixture of stereoisomers. Now, one reason these Wittig reactions are so incredibly useful is that the Wittig reactions can be generated from really common precursors, alkyl halides. So, alkyl halides are really common, they're pretty cheap. And they can make these Wittig reactions. And so this is how we synthesize those reagents that we used. And so let's look at the mechanism for kind of how this works. So in the first step, we have our alkyl halide, and it's treated with triphenylphosphine, right? And triphenylphosphine is just C6H5, or I'm just going to use a phenyl 3. Okay, if you like the C6H5 or you want to draw it all out, be my guest. But this is the reagent. Okay, and what happens is that in this step, the very first thing that happens is an SN2 reaction, where the phosphorus here comes in and attacks that partially positive carbon, and those electrons, and the bromine is the leaving group there, and those electrons go on the bromine. So we have an SN2 reaction. So when we have an SN2 reaction, what we see, right, is 2. Now we have our phosphorus, and I put parentheses, but we don't necessarily need parentheses, phenyl 3, and now our phosphorus has that positive charge because we've got an additional bond there. Okay. Now we also have a hydrogen here, so I'm going to draw that hydrogen out because the next step is a proton transfer. And so with the proton transfer, I want you to notice here that we're using an alkyl lithium. Alkyl lithiums are really strong bases. Now, the lithium itself, right, dissociates, and we end up with this CH2, which has a negative charge because lithium has dissociated, CH2, CH2, CH3. So there are 4 carbons there, and we have 4 carbons. There are 4 carbons here. There are 4 carbons there. I always personally like to double check because if I'm going to make a mistake, I'm going to leave out one of these carbons. So I'm always counting my carbons to make sure I'm not making a mistake. So at this stage, because this guy right here is a very strong base, in an acid-base reaction or proton transfer, he's going to come in and he's going to steal that proton, and those electrons are going to go back on that carbon. So that's a proton transfer. Once we have the proton transfer, now we have a negative charge on that carbon, and that's our Wittig reagent. We've generated it. So this is taking that alkyl lithium reaction that we previously learned, as well as an SN2 reaction, and now you can see how we can synthesize a Wittig reaction that can then go on to be used to turn carbonyls into double bonds, which can be used for electrophilic addition reactions. Now, we do have some limitations to this reaction, okay? Because the first step of the mechanism is an SN2 reaction, a tertiary substrate doesn't work because it's a backside attack and there's too much steric hindrance, okay? So that's an issue there. Additionally, when we look at this, the carbon atom has to be bonded to the leaving group that possesses at least 1 hydrogen. So you need 1 hydrogen on the carbon bonded to the leaving group. For the proton transfer, that next step to happen, right? So 2 kind of things here, but the take-home message is this does not work with a tertiary alkyl halide. Steric hindrance, and we need a hydrogen for a proton transfer reaction. So let's do an example problem. So how could you synthesize Ch18, which is shown here, okay, using butanol as your only source of carbon, which is shown here? So when we look at this, if you have a ketone or aldehyde and you have a double bond, then Wittig should be the first thing that comes to your mind, okay? I want you to notice we have 1, 2, 3, 4 here, and then we have 1, 2, 3, 4, 5, 6, 7, 8 here. So when we undo the Wittig reaction, because it forms a double bond, we are going to undo this sucker. Let me use a different color right there, okay? And so when we go through and we undo that, so let me redraw it. And we think about how, okay, we're going to undo it there. What would those precursors be? Okay, so if I needed to undo this, what would my precursors be? Well, out of the gate, one would be the butanol there, right? But we need to think about when we form that double bond, and we're going to use a Wittig reaction to do it, what group is attached to our Wittig reagent, okay? And so this is a case where, okay, there's that, there's the carbon. Oop, I'm going to go ahead and do a stick structure here. There's our phosphorus, phenyl. Now, I want you to notice we are not showing a hydrogen here, but that would be a hydrogen because we only want to put a straight chain on here. If you're only going to put a straight chain on, then that other group off that carbon is a hydrogen, and it's understood, it's not shown. If we needed any sort of branching, then we could, instead of using a precursor with a hydrogen, we could use the hydrogen there. So now, remember, for whatever reason, we're in this situation where we only have butanol as our precursor, and we also need to make this reagent, the Wittig reagent itself. And so now that we know which Wittig reagent we need to make, we need to think about what reactions do we need to do to make this, okay? And so we think about, okay, what do we know, okay? Well, we know that to make a Wittig reagent, you would use an alkyl halide. And in the alkyl halide, it's a SN2 reaction, so this group stays the same, but you just have a bromine, okay? Then what we would need to think about, right, is how can we go from this to butanol, which is the only thing that we have. It's our only source of carbon. Well, we can undo a substitution reaction, right? And when we do a substitution reaction, right, we could use an alcohol group. And then what we could do is undo a reduction. Right. So those are the things that we can undo. Now, we need to now put this in the forward synthesis, okay? And so now we need to go back and think about reagents. So I'm going to come right down here, and we're going to do this in the forward direction. Okay. So we know to go through reduction, we'd use sodium borohydride. I'm going to use ethanol as my solvent. And when we do that, then that's going to turn the aldehyde into an alcohol functional group. Okay. Then we can use, once we have an alcohol, we can use PBr3 to undergo a substitution reaction and synthesize an alkyl halide. So there we are. Then we can come here and use that triphenyl phosphate. And then 2, we can use a butyl lithium. 1, 2, 3, 4, lithium, right? So there's a butyl lithium. And then that would give us don't forget my phenyl groups, VH, 3H3. And then we could do a Wittig reaction where we add the 1-butanol, 4-butanol, 1-butanol, butanol. There we add the butanol. And when we do this, then we get octene 4-ene. Right? Now, I'm showing this as the E isomer. Understand, you would also get the C isomer as well.